The FJ33 is a medium bypass ratio engine, which simply means that 50% or more of the engine's thrust comes directly from bypass airflow. When air enters the engine through the N1 fan, it follows one of two paths, either through the core of the engine or around it. Air passing through the core is first compressed by the intermediate pressure compressor, or IPC, and then is further compressed by the high pressure ratio centrifugal compressor of the N2 section. But just before the air is squeezed down by the N2 high pressure compressor, it passes by a duct that leads to the acceleration bleed valve. The purpose of this valve is to simply modulate the airflow being fed to the N2 compressor, ensuring the flow remains smooth and constant through a range of transient power requests from the cockpit. This butterfly valve is normally spring-loaded open during operation at low power settings. This allows some airflow to be dumped overboard into the bypass air duct, which helps avoid overfeeding and essentially choking the high-pressure compressor. This process minimizes the risk of the engine suffering a compressor stall or surge. As the pilot adds power and the engine begins demanding more air for combustion, the Fuel Control Unit, or FCU, using fuel as a hydraulic actuator, pushes and modulates the butterfly valve to a more closed position, which diverts more compressed air to be fed to the now more hungry high-pressure compressor. From there, the hot and compressed air is sent to the combustion chamber, ignited, and pushed through the turbine section. This turbine section is where energy from the hot, expanding gases is captured by the high-pressure and low-pressure turbine rotors, which in turn drive the forward low-pressure fan and the intermediate and high-pressure compressor rotors in a uniquely closed system. Finally, that same core airflow passes all the way through the turbine section and out the nozzle at the back of the engine, producing a percentage of the engine's forward thrust. Airflow that does not pass through the core is referred to as bypass air. That bypass air flows through a duct along the exterior of the engine core and then through a forced air mixer, which efficiently mixes bypass air with core air. This forced air mixer contributes to engine propulsion efficiency and decreases the noise level of the engine. A turbofan is much more than just the rotary components found in the engine core. There are many other systems to explore, so let's take a look at a few. In the combustion chamber are dual igniters used primarily for engine starting. A single igniter is used for ground starts. The FADEC computer automatically alternates the use of igniter 1 and 2 for each start. For air starts, both igniters are used since an air start is, by definition, an emergency procedure. Fuel is regulated to the combustion chamber by the Fuel Control Unit, the FCU. This is part of the fuel system and is described there in greater detail. The oil system plays an integral role into the engine's operation and consists of a reservoir that holds just over 2 quarts of oil, a reservoir sight glass for checking oil levels, an oil pump, oil filter, electronic differential pressure sensor, and bypass circuit. If the filter were to become blocked, the differential pressure buildup would cause the bypass circuit to open, allowing oil to continue flowing to the engine, and you would receive a CAS message indicating that this has occurred. It's vital that the proper oil be used in your Vision jet. The preferred type for the FJ33 is Mobile Jet 2. Oil should be serviced to the first bolt below the full line to allow for thermal expansion. Bleed air for the Ice Protection System, the IPS, and Environmental Control System, ECS, is taken from the high-pressure compressor section. The IPS and ECS each have their own bleed air port on the engine. The FJ33 also has 4 additional bleed air ports which are not utilized in your Vision jet. The FJ33 also contains an accessory gearbox which provides power to various components serving vital roles in other aircraft systems. These components, or accessories, are driven by a shaft which is geared to the high-pressure N2 rotary group. Mounted on the accessory gearbox is the starter generator, or Gen 1, the alternator, or Gen 2, and the fuel control unit. The oil pumping components are contained within the accessory gearbox. The starter generator is a dual-functioning component. During engine start, it draws power from battery 1 to rotate the N2 section, or high-pressure rotary group, until ignition of the fuel accelerates the engine towards idle speed. At that point, it is driven by the engine and begins to generate electrical power. Last, but certainly not least, is the brains of the engine, the Full Authority Digital Engine Control, or FADEC. The heart of the FADEC system is the main computer, the Engine Control Unit, or ECU. The ECU is responsible for the control and monitoring of the power plant. It automatically adjusts engine settings for optimum performance in response to varying atmospheric conditions and engine parameters. One of the main functions of the ECU is to react to pilot throttle lever inputs with timely and measured fuel delivery to the combustion section of the engine by commanding a fuel metering valve to either add or remove fuel to the annular, the ring-shaped, combustor. It also records faults and exceedances, provides certain automatic engine protections, and generally reduces engine management workload for the pilot. This ECU is a dual-channel system, although only one channel is used at a time. The second channel exists as a backup. As with the igniters, the ECU alternates channels on subsequent flights. The ECU has several inputs, two of which are engine probes referred to as PT2, measuring total air pressure, and TT2, measuring total air temperature. Additionally, 6 ITT, or interstage turbine temperature probes, are installed in a ring around the engine, 3 dedicated to each channel of the ECU. The ECU calculates one average ITT out of all 3 temperatures for the channel in use and then makes engine adjustments based off of that average. Think of ITT as a general indication of the health of the engine, as it will be a key indication for the pilot to monitor during all phases of flight. Because the FADEC is so integral to engine control and safety, and because the engine really can't run without it, it is designed to be powered by redundant electrical sources. During startup and when N2 is below 80%, the FADEC system is powered by the airplane's normal electrical system. However, anytime the engine's power setting is above 80% N2, the FADEC's primary source of power is a permanent magnet alternator, or PMA, located within and driven by the fuel control unit.